Telling us about embeddings of Kac-Moody Affine Grassmannian slices.
Thank you. And thank you all for coming back. I'm stealing the line from yesterday, but given that there's only one talk, I do appreciate it. And thank you to the organizers for the chance to speak. It's a pleasure to be here. I think I haven't been here in 4 years, we're realizing, so it's exciting to be in Montreal. Yes, so I thought I'd just, now it's not advancing. Okay, good. I'm going to tell you about some joint work that I have with Dinakar Muthiah. It's on the archive last year, but sort of the idea here, this is maybe totally different from the talks this morning, but it's a geometric representation theory, trying to use geometry to understand representation theory. And in particular, here we want to talk about the Affine Grassmannian. And specifically, is there sort of a Kac-Moody Affine Grassmannian is the idea. So that's the headline. Here's some sort of rough statement, just to introduce a little bit of notation. The sort of main theorem is that there are embeddings of something called Affine Grassmannian slices in symmetric Kac-Moody types. Okay, so that's what I'd like to tell you about. But just to outline what's my plan here, first I'll tell you what are Affine Grassmannian slices in the first place. This is sort of like the classical story, not Kac-Moody. Second, I'll change gears and tell you about something called Coulomb branches, which is a kind of relatively recent introduction to math coming from mathematical physics, or really coming from physics. And then finally, I'll end the talk by telling you about the theorem that I told you at the beginning. Again, if you have any questions, please feel free to interrupt. Okay, so what are Affine Grassmannian slices? So first, let me just do a little bit of setup, sort of a representation theory talk. So some standard notation. Hopefully not too much. I'm going to work mostly with groups, not Lie algebras, but so let G be some reductive group, for example, SLN, and little g, frac G, it's Lie algebra. I'll want to pick a triangular decomposition, the usual sort of pinning stuff. So, similarly with groups. So this U plus T and U minus are my notations for unipotent, torus, and opposite unipotent. It's kind of funny that it's not the same letters, but oh well. Such is life. Just other notation, the usual things, simple roots I'll call alpha I, simple co-roots alpha I check. I'm mostly just introducing these notations to remind you of one thing, which is that co-weights or co-characters of this torus, the maximal torus, we can think of that as a lattice inside H, the vector space H, the Cartan. And with that convention, just remind you, a dominant co-weight means that you kind of pair positively with the positive part. Okay. And final kind of ingredient, just usual things, is there's this notion of a dominance order on the set of co-weights, which just means that if I have two co-weights, lambda and mu, their difference is like a positive sum of simple co-roots. It's a bit of a mouthful, but there it is. So this is some partial order on this set. Okay. Cool. So we're going to talk about the Affine Grassmannian. That means we need to talk about loop groups. So here's some brief sketch. First of all, just to remind, G, the group, this reductive group, is an algebraic variety. So maybe it's SL2. I cut out by some polynomial equations. It makes sense to take the A points of that for any commutative ring, potentially. So here's just an example. If we put in some commutative algebra A, we can talk about SL2 of A, right? 2 by 2 matrices with entries in A, determinant 1. Makes perfect sense. And so what we want to do is form loop groups, meaning that we're going to put things like a polynomial ring into this gadget, or maybe Laurent series or power series, something like that. So you get these sort of interesting groups. For example, SL2 of A will always be a group. You can multiply these 2 by 2 matrices with whatever ring you want. And so these are loop groups. I'm not going to talk much about this, but it's worth pointing out. These things are actually kind of like algebraic varieties again, or more precisely, they're in schemes. So both of these examples I've written down are not actually varieties per se. They're like unions of varieties in some nice way. But the key point is you can think of them as some sort of topological space. Okay, so that will be sort of important in a moment. I'm going to mention a Zariski closure. That's really the only reason I say this. Finally, just a little piece of notation. If I had a group G, an algebraic group G, we can define a congruent subgroup where So we're starting with power series in a variable z inverse. And if you take this variable z inverse and just sort of set it to 0, or you could say that z is going to infinity or something, that defines a map to G itself, like to C. And I just want the things that are in the kernel. That's what I'm going to denote by G1 z inverse. So you could think that this is something like an element of the group that looks like the identity plus some Taylor series in z inverse. So it's like something happening in a neighborhood of the identity. Final piece of thing to define what an affine Grassmannian slice is if I handed you a co-weight lambda, you can actually produce an element z to the lambda inside the loop group. And it's maybe a little confusing, so I think it's helpful to have this example in mind. Like a co-weight of GLN is just a list of integers, lambda 1, lambda 2, your lambda n. And what would be z to the lambda? It's just a diagonal matrix where you take this variable z and you raise it to the lambda power everywhere. So there you go. In general, it looks like this. It's just, whatever appropriate group you're dealing with. Okay. With all that set up, then, what is an affine Grassmannian slice? So this definition is due to Braverman-Finkelberg-Nakajima. The motivation for this precise definition kind of comes from physics. I'll maybe gloss over that a little bit, but we need to fix two pieces of information. So we're fixing a group for one thing, again. We're fixing everything I've said. We're fixing a dominant co-weight lambda, and we're fixing some other co-weight which is less than lambda. Doesn't have to be dominant. Then this something called a generalized affine Grassmannian slice is defined in the following way. It's a little bit of a mess. I'll just point out that this is all happening inside. This is happening inside G of Z inverse. And so this funny Laurent series group. And there's a lot to unpack here, maybe. So there's sort of two parts. One is involving lambda. One is involving mu. They kind of are happening in opposite directions. So here you're seeing stuff involving polynomials. So the powers are getting bigger of Z. Here you're seeing stuff involving Z inverse. So the powers are getting smaller. Right? And you're intersecting them. So you're kind of like having some sort of bound in both directions is kind of what you can think. But another thing you can think is that this factor right here, this product, again, there's a lot of notation, but this is an upper triangular matrix, a diagonal matrix, and a lower triangular matrix. This is like some sort of Gauss decomposition. So we're saying the matrices we want to look at have Gauss decompositions of a particular form and another kind of condition on their polynomial part. Okay. I wrote it down because it's important to maybe say it, but I wouldn't worry too much if this is a lot to parse. Yes, thank you. This is a Zariski closure. Okay, so this G of Z is a subgroup of here, right? Z to the lambda is an element here. We're taking a double coset and then taking a Zariski closure. So here's where the topology on this space really is necessary. As I said, it's like an in scheme actually, but.
So what you get some closed set in the group.
Yes. Yeah, it's like a closed sub-scheme of this funny group.
Also, affine Grassmannian.
Yes, I'll come to this in a moment. Yeah. Yeah, so there is an important thing. I did put this, sneak this word generalized in here, which isn't appearing anywhere. Just a final comment is, if mu and lambda are dominant, then we call this remove the word generalized. It's just an affine Grassmannian slice. And this is where the connection to the affine Grassmannian really come in. So I'll come back to that point though. Thank you for the question. Okay, I thought I'd give some examples since it's a little bit unintuitive. I think the most important one, and the most intuitive one, is to talk about the nilpotent cone of SLN. So these are just n by n matrices that are nilpotent. Some power is 0. So there's this observation, let's go back to Lustig, which is that this nilpotent cone is an affine Grassmannian slice. So, and it's an affine Grassmannian slice for the group SLN. And well, there's some co-weight data involved, maybe it doesn't matter, but what is the map? It takes a matrix, an n by n nilpotent matrix, and sends it to the identity plus Z inverse X. It's kind of like related to the thing you would write down when you compute the characteristic polynomial. Right? If you compute the determinant of this, it's like very close to the characteristic polynomial. Just a comment. So here's an example of an affine Grassmannian slice, the nilpotent cone. More generally, what you could do is take a nilpotent orbit inside SLN. So those all live inside the nilpotent cone. And we could just restrict this map. And in fact, these also give isomorphisms. So I wrote down some data here. Maybe it doesn't. Oh, sorry, this should be a lesser equals, greater equals, whatever. So I'm saying take a partition of n, call it lambda 1 through lambda n. Here's some affine Grassmannian slice that's the same as that. So you can think that this is some class of varieties that includes all nilpotent orbits of type A, for example. In fact, there's a very nice result of Merkovich and Vibranov. They said that in type A, if we have lambda and mu both dominant, which again is this affine Grassmannian slice, not generalized, then these affine Grassmannian slices of type A are always a nilpotent orbit closure intersected a slow to V slice, or various slices. There's some subtleties here in that this maybe is happening for SLN. Here you're moving to GLM, different sizes. Some funny stuff can happen, but these are a very interesting family of varieties, slow to V slice and nilpotent orbit closure, and we're seeing them in type A. So these are sort of exactly what the affine Grassmannian slices are in type A. Okay. Right. Thanks for pointing that out. Yeah, okay, so there's some generalizations of this statement too. Great, yeah. I don't know what the precise statement is, but it's to some space of matrices, right? I should say, I mean, actually, maybe it's worth saying, they also showed that this same family, like, there's also some Nakajima quiver variety that's isomorphic to these two as well. So there's like 3 families of varieties that are all the same somehow in type A. Okay. Just mention a few properties. So in spite of the complicated looking definition, this is actually a finite dimensional affine variety. The dimension is something. I mean, so if lambda minus mu is, there's supposed to be an alpha I check here. But if you wrote it as a sum of simple roots, you just take twice their sum. So that's missing here again. Sorry. It's probably more typos. What else? So these are actually Poisson varieties. They have some Poisson structure. In fact, they have what are called symplectic singularities. So they're sort of a very nice family of Poisson varieties. I won't touch on this anymore, but just mention. Okay. And this is sort of a key point in this talk, is I started with lambda and mu. If you add a third co-weight into this mix, like mu, nu, lambda, I know they're out of order, like alphabetically, but then the one, you can take a slice between mu and nu, or a slice between mu and lambda, and in fact, they embed into each other. So I'll give an example in just a moment. Simple example. So this is a key point in this talk. It's somehow this actually forms some sort of directed system in a way. And why is that? Well, it's some general fact about these closures. These are like double coset closures, and they contain each other. Somehow the closure order is the dominance order, something like that. Yeah, and this is where I want to give an example. So I already mentioned the nilpotent cone. Maybe I'll just mention this specific example. So here we're taking G to be SL2. One of these affine Grassmannian slices is you take the simple coroot alpha, that's lambda. Again, there's only one simple coroot, it's SL2. We take mu to be 0. Then this is exactly the nilpotent cone of SL2. So it's a special case of what I mentioned before. And just to be very clear, these are 2 by 2 matrices, complex numbers such that the determinant is 0. Very nice variety. Somehow this is like, this cone. If I drew the real points, it looks like this in R3. And just to mention one of these closed embeddings, one of them is actually the cone point here. So in fact, what you can do is take W0, 0. So here sort of lambda was alpha, nu is 0, 0 is mu. So we have like a 3 like this. This is a point. It's the cone point. Exactly, it sits inside. So I'll come back to this in a little bit. But this is kind of the idea. You have some interesting singular Poisson variety. It has some strata, which are the symplectic leaves. We can see some of them as these embeddings. Yeah.
What is W?
It's also a point. Yeah, sort of like a different point in a way, but maybe one sanity check is I gave a formula for the dimension. So if lambda and mu are the same, then this is 0, so the dimension is 0. But
The dimension is even.
yes, dimension's even. Yeah, I mean, you can think about that too. Is when I say Poisson structure, secretly I mean like holomorphic Poisson structure, like a complex Poisson structure. But these things are actually like kind of generically symplectic. So the dimension should be even. Dimension should be even, and so it should be like, yeah. The complex dimension is even. In fact, these are expected to be hyperkähler varieties, I should say, but I don't know much about this. So it's a real variety, it has dimension 4, multiples of 4. Any other questions so far? Okay, so let me return then to your previous question. What does this have to do with the Affine Grassmannian? So the Affine Grassmannian of G can be written as follows. So you take Laurent polynomials, mod polynomials. Often it's not written this way. It's written as like Laurent series, mod power series, but they give the same thing. Of course, the Affine Grassmannian, if you know about it, can be written in various ways. It's like some modular space of bundles, blah, blah, blah. There's various pictures, but let's just stick with this one for now. This is, so we're taking a group, we're taking a quotient at some homogeneous space. In particular, what we could ask about is like, how does it decompose into orbits for various groups? So this has some sort of like a kind of a Bruhat decomposition, but it's called the Cartan decomposition. I mean, it's like a parabolic Bruhat decomposition. And it turns out that the orbits are labeled by dominant co-weights. The same combinatorics is showing up again and again, not a coincidence. So what we get are Schubert varieties by taking closures of these orbits. Again, these are like parabolic Schubert varieties, you could say. So we're taking orbits for parabolic secretly. If you want to think of an analogy to a finite dimensional flag variety, it's kind of similar, but these closures called Schubert varieties, they are also finite dimensional varieties. They're singular. In fact, they're projective. And so this is what people are often very interested in. So what is the link to this slices I was mentioning is if you have mu and lambda both dominant and they're less or equal to each other, then these Schubert varieties are contained in each other. This is the order on Schubert varieties. And you can ask, if I have an inclusion like this, can I produce a transversal slice between the smaller variety and the larger one? And this W lambda mu thing is a way of producing it. So there's some general recipe if you have like even a Kac-Moody partial flag variety for producing transversal strata and slices and stuff. And this actually fits into that story in a way. So, and why are we so interested in all of this? Well, here comes the actual representation theory side. It's through something called the Geometric Satake correspondence. I'm going to phrase it in a way which involves slices first before returning to the usual statement. Okay, so that'll be important later. So inside this W lambda mu space, there's something that, stealing Joel's notation, I'll call W lambda mu plus. You remember perhaps that there was some sort of Gauss decomposition. Here I'm throwing away everything except for the final factor. So only should involve the like negative lower triangular stuff. Okay. Then we have the following result. I mean, it's due to a lot of people. Maybe in the present formulation is kind of Merkovich-Valonin, but Vasa has contributed by observing that generalized slices fit into this picture. So I will add Khilaf. Says the following statement. So we take a lambda and we fix it. Then you can look at all these different slices. So for all different mu, which are less than lambda, all the varieties I was just describing. You take these plus varieties, you take their top or more homology, you add that all together and you get a representation from it. And the claim is what representation? It's actually a highest weight module with highest weight lambda. However, you'll notice that I was talking about co-weights. Co-weights are like weights for the Langlands dual group. So there's like a Langlands duality here. So co-weight lambda. Okay, so there's a lot going on here. But maybe one thing to mention is just that for a given lambda mu, you should think that this is just, I mean, that's what I'm trying to indicate here. These are the weight spaces of some representation. So the Affine Grassmannian slice is like a geometric version of a weight space. Okay. Very famous statement. Again, this is not the maybe usual statement of this result, but this one is useful because it will be useful later. So geometric Satake correspondence with a question mark. Well, again, if you've seen the geometric Satake correspondence before, that maybe doesn't look quite right. The usual statement is something like this. You look at G of O, oh, sorry, this would be G single bracket Z, but anyway, G of O equivariant perverse sheaves on GER G, and that's a tensor category, and that's equivalent to this tensor category of representations. And the precise correspondence is that the IC sheaf of GER lambda bar goes to V lambda. So this is the usual statement, but can be used to prove this one. So they're somehow like the same in a way, but why am I explaining both? Again, this is maybe what some of you have seen before. It's a very famous statement in geometric representation theory and the Langlands program, etc. But it's because I want to talk about Kac-Moody types. Okay, and if we suddenly change gears and say, what if G was a Kac-Moody group? That's the question. Not affine, yeah. Just so yeah, really start with a Kac-Moody group, and we're going to try to take the Affine Grassmannian of that, and sort of it's hard to make sense of what that means. So there's no geometric Satake, at least naively, it's like kind of complicated. But there's this proposal, which is I think goes back to Braverman and Finkelberg. Instead, maybe it would make sense to try to define these Affine Grassmannian slices. We might have better luck doing that. Well, in fact, it seems that we have better luck doing that, and aim for this statement instead, the previous one. Okay, so you don't try to make an Affine Grassmannian, rather you try to build all these slices and put them together to make the statement.
What is G?
G. Oh, I'm sorry, Langlands dual. Langlands dual. Yeah, so maybe we should be careful. Maybe we mean the Langlands dual Lie algebra. Maybe we mean.
Let's take one dimensional group, you know?
Yes, yeah.
And here you suggest to take the whole completely.
Yes, yeah. I mean, this should be some sort of integrable representation, so you could think that it integrates to the group. I'm being a little schematic here, but.
Even in the case where the G was affine Kac-Moody, you would still be doing something different than
Yeah. So
Affine
you
Grassmannian.
Yeah, that's right. Yeah, that's right. I mean, if G was affine Kac-Moody, you already have a loop, right? Now you're adding another loop by getting to the Affine Grassmannian. So this is what Braverman-Finkelberg called a double Affine Grassmannian. So even for affine Kac-Moody, this is already something quite complicated, and still, I would say, kind of poorly understood. But any other questions at the moment? Okay. Yes, that brings me to the next topic. So again, this is sort of motivation. So we have this family of varieties, just to summarize. They're labeled by some representation theoretic data, the lambda, mu. They're interesting for various reasons. I mean, for one thing, we're getting some familiar spaces from it, but also we have this nice geometric interpretation in terms of representation theory, or we hope to anyway. So that's sort of the main motivations for what this project was. Okay, so right. The proposal was that you should try to define W lambda mu. And for affine Kac-Moody groups, Braverman and Finkelberg did have a proposal, something called Uhlenbeck spaces, but in general, it's sort of just open. Can you do this is the question. And this is where these, whatever Coulomb branches are, enter. So, and here's a brief overview. This is not doing the topic justice, but. So again, G is a connective reductive group, same data. But now we're also fixing N, a representation of G. This is sort of some input data here. So Braverman, Finkelberg, and Nakajima, a lot of the same people are going to reappear again. Anyway, and for that reason, I'm going to abbreviate it BFN. They construct an affine variety, which is called the Coulomb branch, from this data. So MC of Gn. It depends on G on N. And from vague impression, this comes from physics. Physicists associate some sort of quantum field theory to this data. In fact, it doesn't just depend on N, it really depends on N plus N dual. So there's some loose dependence on N slightly, but we can gloss over this. So this is a relatively recent development in mathematical physics from 2015. A priori, it was physicists had been studying these varieties, but it was hard to make sense of what they are. And so the sort of groundbreaking work of Nakajima and Braverman-Finkelberg of Nakajima showed that there was some way to actually construct an algebraic variety. And this is not going to help very much, but I'll just say, how did you define this a little bit? Well, it's actually something also involving loop groups, funnily enough. So G of Z, N of Z, etc. And not worry too much, but they're building some sort of BFN space. Recently, I learned that Nakajima has called this the BFN space in some of his talks, but for referencing to bundle, framing, and N, because where bundle is coming from G, because we're dealing with loop groups, the framing is this is the Affine Grassmannian, and N is this N. Anyway. Okay, but so it's some sort of infinite dimensional space. It's like very infinite dimensional in that it's not it's an in scheme of in infinite type, but somehow they can define its homology. So you build some space, you take the homology of that, equivariant Borel-Moore homology. We call this A. I'm glossing over lots of things, but somehow this has a ring structure. You can look at their paper. It's defined in geometric terms. So there's some way of relating these various spaces to define a multiplication in terms of homology, like push forwards, pullbacks, etc. It's like a convolution algebra. And they prove that this is a commutative algebra, and you can take its spectrum, then we get an algebraic variety. I mean, technically an affine scheme, but it's actually irreducible, reduced, etc. And so in fact, they show various things, like in spite of the complicated nature of the definition, it's an irreducible normal variety with a Poisson structure and blah, blah, blah. There's word sequencing. In fact, sorry. Yeah, in fact, it's finite type. Yeah, that's right. Yeah, so it's a finite-dimensional variety. I meant to add this, but Gwyn Bellamy recently showed that these all have symplectic singularities. So it's some huge class of symplectic singularities. Very interesting construction. So what's the link to what I was talking about before? So it's another theorem of BFN. We start with a quiver. So maybe this one. So you should think that this is an oriented Dinkin diagram, right? This is like SL5. And we do something that looks, well, if you know what quiver varieties are, it may look familiar. We're going to take some dimension vectors and some framing. And so we can think of that as some numbers like 1, 2, 0, 8. I'm just labeling the numbers here. And from that, they define a group and a representation. Okay, the group is like coming from the circles, and the representation is coming from the arrows. So the group is just the product of GL5, GL2, GL7, GL7. And the representation here would be like all of the linear maps between the various arrows, or sorry, corresponding to arrows. Okay, so this is exactly the sort of input data we can feed into this Coulomb branch machinery, which we're just using as a black box here. And they prove this remarkable theorem. So we start with an ADE Dinkin diagram, and V and W, the exact data from the last theorem. The Coulomb branch is an Affine Grassmannian slice. All right, generalized. And so I want to highlight this. There's two groups here, and it's very confusing. G now is a product of GLVs, okay, from the quiver. And the group that you're going to get out, like the slice, is the ADE group from the Dinkin diagram. So there are actually two groups, confusingly. Yeah, it's very confusing in a way because the construction of the Coulomb branch uses loop groups. So sort of like the Affine Grassmannian is involved here, but we're also seeing the Affine Grassmannian over here, but they're different groups actually. And this V and W data, they encode the co-weights actually. Lambda and mu are somehow read off. So it doesn't matter exactly, but lambda minus mu is these VIs, same notation I had before. Another comment is actually this independent of the quiver orientation. So you can just flip the arrows around, it doesn't really matter. Okay. It's all pretty weird, so I wanted to show some examples. So we mentioned before, the nilpotent cone is a Affine Grassmannian slice. So from this theorem, we should be able to write down a quiver corresponding to it. Well, it's this one. It's like a kind of complete flag, 1 through n. And I mentioned before also that nilpotent orbit closures in SL. Well, this is in SL5, right? I'm saying a nilpotent orbit with the Jordan type 311. This is an Affine Grassmannian slice, and well, here's the quiver. When I wrote it this way, it's maybe not so transparent how I'm getting these numbers, but it's nothing too complicated, honestly. It's just a mess of combinatorics. Okay, so you can think, though, because of this BFN result, that if you never knew what Affine Grassmannian slices were, etc., if for some reason you knew what Coulomb branches were, we could have started with this input data, and we'd get these interesting varieties out of it. And that's sort of the key idea here is the quiver could be anything. Okay, so what about this quiver? I just pick some random. So this is a Dinkin diagram for some Kac-Moody group. Okay.
So consider all the simpler worst case.
You can add double edges. I thought it might look confusing, but yeah. So symmetric type is fine. You could add multiple arrows here, for example. Yeah, that's allowed. With Nakajima, I don't mention this, but Nakajima and I came up with a way to deal with symmetrizable type too, but I'm not mentioning it because we can't prove as much about it. But yeah, symmetric is okay. Yeah. Maybe I should have included some multiple edges here just to highlight. But yeah, thank you for the question. So the idea is, yeah, this Coulomb branch construction doesn't care what your Dinkin diagram is. In fact, you can have like, you could have edge loops here, you could have the Jordan quiver, you could do anything. And so, but what they propose is, say you want to study a symmetric Kac-Moody type, maybe this Dinkin diagram, we can define Affine Grassmannian slices now. Just define them as Coulomb branches. It's an interesting definition. The question then is like, does this actually work? Does this correspond at all with what we know and love, or possibly love, about Affine Grassmannian slices? I think you could think that, I don't know if this is the right thing exactly, but there's some Borchard's algebras or something built out of other quivers. Like there's some interesting variety. I think you could think that it comes from representation theory still, like if you had the Jordan quiver, but maybe I won't try to precisely spell out. I think you could really think that it is like a Affine Grassmannian slice, but yeah, that's a great question. Yeah, certainly they seem to be interesting. That's maybe the motto. Okay, and so just in particular, we're again now when I'm writing all this stuff, when I write this, I mean define it as a Coulomb branch. This is a Coulomb branch. We can still make sense of this plus thing. We could hope that this is exactly giving what Braverman and Finkelberg had suggested, some sort of spaces that let us build representations. And I'll just mention that, so in finite type, this is known. I mentioned already, this is geometric Satake. And in fact, it's also proven in affine type A. So Nakajima showed that in affine type A, this also works. You can build representations of SLM hat, stuff like that. Affine type A is quite special because there's something called bow varieties that Nakajima has studied with his collaborators, and they give an explicit geometric model for what this Coulomb branch is. So it's something like a quiver variety, but not exactly. So but it's important that you have this model. So in general, though, if you wrote down some random Dinkin diagram, it's really unclear what the geometry of this thing is at all, because this Coulomb branch definition, I went over it very quickly, but I hope the takeaway was that it's a little bit opaque. Okay, it's the homology of something or other. You don't really know what it is. It's a bit of a mess. Okay. Yeah. So the top row more homology. I guess we could just say it's like take the irreducible components of this and take their span, and yeah. Well, in finite type, it's pure. So there's no other component dimensions. I don't know offhand what the total Born-Moore homology is. So I think there's a Satake answer, but I don't know. It's an interesting question. Yeah, I don't know. Okay. So with all that said, I'd like to turn to the final result, our main result, which is just basically to say that, well, at least one aspect. So again, we have some proposal, right? You use Coulomb branches to define things. We want to check that works. The sort of sanity check we have is that, in fact, you can get these close embeddings out of it. And maybe there's some little bit you have to say. So again, same sort of idea, just like what I was sketching here. You have lambda, mu, and nu, and they must correspond. There's one extra caveat we have to add, which is that, so I mentioned before that when you have this triple, I can look at the slice between mu and nu, and mu and lambda. There's one more I could have done, which is nu and lambda. And here we need that one to be like a cone, okay? So I'm going to skip mostly about what this means. Well, I'll address in just a second. So, and part of the theorem is also that in finite type, we recover the usual picture. Okay, so it's an extension of the finite situation to sort of any symmetric Kac-Moody. Okay, just one comment is, again, there are three things, right? Mu and nu, mu and lambda, nu and lambda. You should expect that nu and lambda is like the transverse slice from this thing to this thing. And there's a general principle in this Poisson geometry, it's kind of due to Coulomb, that the transversal slices to sort of leaves should be cones. So this final condition is just basically imposing that, and somehow that it goes into the construction. So, okay, so right. Okay, so I just want to emphasize everything is defined in Coulomb branch words. So I have one Coulomb branch algebra, I have another Coulomb branch algebra. We want to build a map between them that's surjective. That's what this closed embedding is saying. We don't build that geometrically, so this is homology of something, that's homology of something. You might hope to do some sort of correspondence in homology, like push-pull, something like that, but this is not what we're due. And I just want to highlight sort of like try to sketch the difficulty of that, because so for example, this is the nilpotent cone of SL5. Here I'm taking a nilpotent orbit of a partition of 5, so this is a subvariety of this. Okay, and the quiver data look kind of like different. Okay, and you can build things that look like totally unrelated, seemingly, or at least naively. So somehow we need to take this input data and surject onto this input data. I just want to highlight it's a little bit strange thing to do. At least I think so. So instead, our approach is kind of entirely algebraic. So in the last 10 minutes or so, I just want to highlight like kind of the idea, and also I think try to connect that back to reality a little bit, things that are more familiar sounding. So there's something called fundamental monopole operators. So monopole operators is a terminology coming from physics, but in mathematical language, there's certain elements of this ring, and more precisely, they're like some equivariant classes of something or other. We can say more precisely, but I don't think we have time. And I'll just mention that there's some like easiest ones you could possibly write down. In the context of quivers, Muthiah and I have taken to calling them fundamental monopole operators, but somehow they come from, well, minuscule co-weights of the group G somehow. So anyway, there's some picture and there's a way to write these down. And you can prove that in the case of a quiver, these fundamental monopole operators, FMOs, they generate the coordinate ring. Okay, so, and finally, maybe another input is actually they're quite explicit. Okay, and the exact details here don't matter. I'm only writing this down just to say you can write down some formula for these things. Okay, so in spite of the fact that this whole construction is very opaque and like homology of some infinite dimensional space and blah blah blah, you can make this kind of precise. It's a little bit tractable to deal with these particular elements. Okay, and they generate the ring. So we don't know the relations between them, but we know they generate. Okay, so we use these as our tool. This is our tool for actually dealing with these rings. So in finite type, maybe forget this for a moment. Again, I had one slice embedding into another one. This is the classical picture in terms of loop groups that I mentioned at the very beginning of the talk. But Braverman-Finkelberg-Nakajima tell us that both of those are Coulomb branches, right? Again, I drew some quivers just a moment ago. And from the previous slide, you have these funny functions, right? So you have funny FMOs here, you have FMOs here. And we showed that actually under this diagram, they just restrict, oh, sorry, too far. They restrict, like, so those monopole operators here restrict exactly to monopole operators there, or they restrict to 0. It's very predictable and explicit. So this is, again, so giving some link between finite dimensional situation of finite type Kac-Moody group and the Coulomb branch picture. And so what we did is just take this as an ansatz, right? That this is what should happen in all types, and that's how we prove the result. So you just define, well, a priori it's not even a ring homomorphism, but you define a map on the coordinate ring here to the coordinate ring here, which sends them to themselves. And we check that that actually is an algebra map and it's surjective and etc. So it's a little roundabout, but again, it's very algebraic. Okay, almost on. Ah, yes. So you can do a little bit of variations on this construction that are related to something called Zastava spaces. And there you actually can build ring maps, it turns out. But I mean, I don't know. I'd like to have a better explanation for this. We ultimately write down some long sequence of maps and you check that it has this effect, and then so we do actually construct like a birational map between them or something and check that it has the properties, and then it's surjective, and yeah, I don't have a better answer. Okay, so just an aside about why I think this algebraic approach is useful, or maybe why it's a little difficult to do it geometrically. It has to do with quantization. So Coulomb branches admit deformation quantizations. So geometrically, you do that by turning on or introducing some extra loop rotation, and you work with equivariant homology with this extra loop rotation. and you end up with an algebra that's like an algebra over the equivariant coalomb of a point, which is just this polynomial ring C of H bar. So we have an algebra over C of H bar. It's not commutative, it's associative. But when you kind of specialize H bar to 0, you recover the original ring. So it's a deformation quantization. This is where the Poisson structures are coming from, actually. Okay, so for quivers, we actually get some very interesting algebras here. And in general, for Coulomb branches, you get lots of interesting algebras. For quivers, though, you get things related to Yang-Yus. No, so a finite type, I would say any quiver. Yeah. So even if you start with like a finite type A Dinkin diagram, in general, you can write down something. You can write down something. Maybe we can talk more after. Yeah. So something like a Yangian coming from your Dinkin diagram. And okay, so this is a little bit of a naive statement, but I'll just say that when you have an inclusion like this, like we're talking about, it's not always so easy to quantize this, at least not in some naive sense. So let me give an example in a moment. But what I'm essentially trying to say is, again, we're dealing with homology of something or other, homology of something else. And maybe you would hope to build like a correspondence between them. That's how usually this sort of thing would be done. But it can't be something too naive, because if it was, I could just add loop equivariance and then I would quantize it. And I'm claiming that you can't do that without like a little bit of fine tuning of things. So maybe let's just illustrate an example. Let me do this example. Okay, so in this case, so for this nilpotent cone of SL2, this algebra A of H bar, well, maybe I'll set H bar to 1 just to not deal with H bar. This is like the enveloping algebra of SL2. So this is a truncated shifted Yang, whatever that is, except for that you have to specialize at a central character. And it's the central character that's like invariant. I mean, I forget the name of that one always. It's the quotient where the block of category O has like 1 highest weight. Anyway, sorry. Oh, that's okay. And well, this variety here is a point. So its quantization should just be like C or something. So for this A of H bar equal 1, it's just going to be C. And the point is, again, this particular central character doesn't, this algebra has no finite dimensional representations. There's no map like this. So again, Ben Webster has told me that maybe you should think a little differently about this, but anyway, at least naively, there's no like way of doing this. So, okay. How much time do I have? A couple minutes. Okay. So maybe I'll just end with two comments. One, just to tie this to the talks from this morning, is I think this is a really interesting topic, but I don't know much about. Is you can do something called a K-theoretic Coulomb branch. So you can take the K theory for G, Z, just do the exact same story. Instead of getting Yangians, now you get things built out of quantum affine algebras. And I'll just highlight that Schrader and Shapiro, they show that the algebras you get here are like cluster algebras, or they're related to cluster algebras. So as I mentioned, this is something like a quantum affine algebra or a truncated shifted quantum affine algebra. So it's like a trigonometric version if the Yangian is a rational version. So some interesting story. Anyway, that's the only link to the talks earlier that I can think of. Final comment, though, is the final slide. So just to recap, we started finite AD type. We used loop groups to build some variety I called W lambda mu. Okay. Then we saw that Coulomb branches let you realize the same variety. And you have these interesting functions called fundamental monopole operators. Okay, we don't actually know what they are. We don't know what they are as functions on this space. And even in the very simplest case, for example, we know the nilpotent cone is arising in this whole story. So we should have all these fundamental monopole operators functions on the nilpotent cone. We don't know what they are. And it includes lots of natural things like, if you take an element, a matrix in the nilpotent cone, you can look at the matrix entries. Those are functions. You get all of those. You get the Gelfand-Cetlin integrable system. Somehow that comes for free the way this is constructed. And more generally, if you take like the identity plus Z inverse X, the thing I was mentioning before, you can get some minors of this. And you can like extract coefficients of them. So it's like a very natural family of functions, but somehow even here we don't know what they are. However, I think that our theorem is, the model I'd like to advocate is that these should be quite interesting because they restrict along these funny embeddings. I mean, the whole story I've told you is our theorem anyway is built out of this result. So maybe the question is, can someone tell me what they are? So okay, and I'll end with that. So thank you. And I couldn't resist putting my favorite quote in this matter. It's just Douglas Adams anyway.
Are there any questions? Because we won't get any.
I guess I'm curious about this FL2 example. I mean, so initially you would expect it to be a kind of morphism between definitions, right? And the other quotients of USL2 would give you the one that you
Yes.
expect. Do you think there should be some way of kind of twisting the bigger deformation so that it is more functorial?
Like there's one way which is very natural actually in this Coulomb ramp picture is to introduce something called flavor symmetry, physics terminology. And then you would get the other deformations of USL2. So you can actually get all of these. Yeah, you can change this. You could get the whole family if you wanted. You could get all these things. So yes. It plays a role naturally also in this picture. I just skipped over, but still I think it is fair to say that at least if you naively interpret it, it's going to be hard to try to build a correspondence between them. I think
So it's kind of not functorial.
yeah, that's my impression. I mean, I'd like to be wrong. So
Yeah, I mean, I think the suggestion I had made is that you should think about this in terms of primitive ideals. Organization.
yeah,
We know that if you're primitive ideal, that you're stability. There's that quotient is a
True. yeah. Like if you put a general thing here, maybe it does have some finite dimensional modules, and then you could sort of get like some matrix algebra here, something like that. This you could build, right? And yeah, but of course that's not literally what the quantization of a point is, but it's like Morita equivalent, etc. So
Yeah.
it's quite similar, but yeah.
Can you compute some example, like kind of the
What these functions are, for example, or
yeah, Grassmannian graph too.
oh yes, there are some interesting examples, and there's some physicists who study the same sort of question. Excuse me, like Hanani and some of his collaborators, and thankfully we can rely on them because somehow physicists can compute like remarkably what these things are. Like you write in down some random hyperbolic Kac-Moody thing, and they might tell you what the variety is explicitly. And indeed, these are recovering some natural embeddings of them. So yeah, I don't have a good example off the top of my head, but they're interesting varieties. Yeah.
I'm sorry. So in your list of things, maybe when you say fundamental monopole operators, I don't imagine quite the same thing. You mean decorated ones?
Yes. Yeah. Dressed. Yes, I should add the word dressed or something.
Oh.
There's quite a few of them. Yeah. So it's a lot of functions, but yeah.
Do you know that you don't get every function?
I mean, they do generate the ring. So I mean, here, for example, I could tell you what they all are, but it's like the entries and that's it. Yeah. Those are the fundamental monopole operators, basically. So they generate, but it's just a little bit unclear exactly what.
But I think the question was, might they be the entire ring?
Oh, I see. Sorry.
We know basics,
No.
and we know that there are many things.
Sorry.
Okay.
Yes, they do not span. No. There are other more monopole operators in physics, they would say. Mathematically, it's a little bit, hard to say. There's some choices involved, but those actually span the ring. So there is a basis for the ring you could write down, but it's not the fundamental monopole operators. They're only some part of that basis.
You also mentioned this property that W lambda nu should be conical. Is it possible to say like precisely what it means in terms of lambda and nu?
So yeah, we can say an affine type. Well, I can say it in words. It's just the level must be 2 or more. So if the level is 1, then you can get some affine Grassmannian slices that look like C2 with the symplectic structure. So it has a cone point, but it's like not a Poisson cone point, something like that.
And
So
like even though
yeah, and so an affine type Yeah, this W lambda mu. I mean, okay, conical for the usual gradings that we would look at. Yeah. Level. Whoops. Level greater than 2. Level 0 is like hopeless. That's bad. Level 1 is ugly in the physics terminology. The good, the bad, the ugly. Anyway, so yeah, physicists love these like terms. So
You know, remind me, like I had at one point convinced myself that it was exactly the flatness of the moment.
I think it's related to this too, right?
I'm trying to remember. I feel like there's something in your paper, maybe in something in faculty that you cited. That
Yeah.
suggested that it wasn't quite exactly the same.
Right. I don't know if that's like proven or not. It should be proven somewhere. Sorry.
It's like if it's not good,
Yeah.
then it's clear that the moment now isn't flat. Maybe that's maybe the other way around.
Right. I think that's the case. Yeah. But I don't know if it's wrong or not. I can't recall. You're getting conditions on this goodness that are very similar to the conditions that like Crowley-Bouvier wrote down, but I don't know. It's a good question. Maybe I should have refused to answer it on the grounds that I. Yes. They so physicists associate some three-dimensional quantum field theory to this input data G, N, or okay, they would say the compact group and the N plus N dual, but it doesn't really matter. So it's something they would talk about very concretely. There's some fields, there's some Lagrangian, there's an action, it's all the usual quantum field theory stuff. They're looking at the vacua of that theory. So like minimizing some energy function. And they say that this space of vacua has like some components, and one of them is the Coulomb branch. And another one is called the Higgs branch. The Higgs branch in this quiver setting is a Nakajima quiver variety, actually. So it's another very familiar variety. The name Coulomb and Higgs have to do with like what's happening to the fields when they talk about these components. Like some of them are 0 here, some of them are 0 there. It's like reminiscent of what happens in electromagnetism, I guess. So, but beyond that, I can't really say much. It's confusing. I mean, it's to me. I don't know if you maybe.
It's about like the Higgs mechanism, which I think like actually means like the stabilizer. This turns out to be like this experience really stabilizer. Maybe just a tiny addition to what Alex said. I don't know if it will actually be helpful. So you have this 3D theory, and this is a big kind of quantity thing where you're looking at like maps of a 3D manifold into cotangent stack, yada, and you're supposed to use some that. Like as far as hard to do that. But there's sort of part of this theory that's easier to understand topological. There are actually two parts that come from one of the two topological twists. And so the Coulomb branch and the Higgs branch are describing what's happening in these two topological twists that kind of pick out two pieces of the space.
I mean, my impression too is that somehow even in physics, it's slightly opaque what they are. And for example, these multiple operators are like very important, or at least to certain physicists in like capturing what it is. Certain multiple operator has some very specific meaning, like you're inserting some sort of operator that's like a point operator or something. And yeah. Thankfully, Braverman-Finkelberg-Nakajima somehow converted that into some mathematical thing. So